Stare at a standard geological map, and you are immediately hit with an overload of information. Thousands of contour lines, cryptic symbols, and overlapping colors fight for your attention on a completely flat piece of paper. But that two-dimensional image is a mathematical illusion. Every line and color on that paper is actually a highly compressed three-dimensional data matrix. The Pragoic II syllabus, the second practical coursework in cartography and surveying, requires constructing this matrix from absolute first principles. To understand how it is built, we have to deconstruct the flat image, pulling it apart into three distinct structural pillars. The foundation is the base geometry. This is a purely mathematical grid, known as a map projection, that dictates how the Earth's curvature is translated to a plane. The middle layer is surface analytics. This consists of the physical topographical survey data and the terrain quantification that plots exact elevations. The top layer is the subsurface structure. This maps the hidden geological deformations, the unseen rock layers shifting beneath the soil. A functional two-dimensional analytical model of the Earth is only possible when these three layers mathematically interlock. The foundational geometry problem of all cartography is that it is physically impossible to flatten a three-dimensional sphere without violent distortion, tearing, or stretching. The conceptual solution is to abandon flattening the sphere directly. Instead, mapmakers wrap a mathematically predictable two-dimensional shape, like a cylinder or a cone, around the three-dimensional globe. When a cone drops over the globe, it touches at the standard parallel, locking scale perfectly with zero distortion. To map larger regions accurately, mathematicians modify the cone to intersect at two distinct rings. This conical projection distributes mathematical accuracy over a wider area. Complex territories require advanced algorithms. The Bond projection modifies parallel spacing, while the polyconic, or Bahulakar projection, stacks infinite cones along a central meridian. This polyconic method calculates a unique cone for every single line of latitude, making it strictly necessary for accurately mapping regions with extreme longitudinal stretches. A projection is a rigorous mathematical prerequisite. Without resolving this geometry first, any data added to the map lacks scientific validity. Once the flat geometric grid is mathematically sound, the mapmaker must apply physical, three-dimensional topographical data onto that foundation. Before a single contour line can be drawn, accurate baseline elevation data must be physically gathered in the real world. This begins with the dumpy level survey. A dumpy level is an optical instrument secured on a tripod, used by cartographers to establish perfectly horizontal sightlines and measure precise vertical elevations across uneven terrain. Once thousands of these raw elevation data points are gathered, they must be mathematically quantified to serve any purpose for topographical mapping. Look at this grid overlay representing Wentworth and Smith's method of slope analysis. It quantifies terrain steepness by counting contour line intersections within a grid. This calculates an average slope across a designated area, yielding a broad metric rather than measuring isolated hillsides. The cartographic requirement is to understand the statistical distribution of these newly calculated slopes across the entire region, turning geography into statistics. This graph applies a Lorenz curve to plot cumulative land area against cumulative elevation, showing how steepness is distributed. Plotting trend lines onto these graphs exposes severe geographical anomalies that remain completely invisible to a surveyor on the ground. Surface mapping relies on the rigorous translation of physical dumpy level measurements into actionable statistical topography. Below the mathematically analyzed surface terrain lies the hidden third layer, subsurface geology. If the Earth were static, rock strata would stack in perfectly flat horizontal layers. But tectonic forces create a dynamic, chaotic reality of constant deformation. The ultimate cartographic challenge is compressing these massive three-dimensional structural anomalies onto the mathematically flat two-dimensional surface we just built. Watch what happens under extreme tectonic pressure. This is a fold, or vallate. Rock layers buckle and bend upward or downward due to horizontal stress. When the pressure exceeds the rock's flexibility, it fractures. This creates a fault, or branch,
which is a physical fracture that aggressively offsets rock layers and creates sharp breaks in the map's continuity. The unconformity, or Visham Vinyas, represents a gap in the geological record where erosion removed older rock. Looking top-down, this represents millions of years of missing history. The map uses standardized symbols, Bhu-Vayagyanik Olut Chin, compressing these faults, folds, and time gaps into a readable syntax. By locking this final geological layer onto the mathematical grid, the geographical map transforms into a functional model of the Earth's violent, unseen structural history. The mathematical projection, the surface analytics, and the geological strata are not separate entities. They snap together into a single, unified analytical tool. Their interconnectedness is absolute. The subsurface geological symbols rely on the topographical surface analytics, which in turn rely entirely on the exact mathematics of the projection grid. Proving you understand this interlocking matrix is the objective of Dr. Kusum Mathur's Pragoyik 2 assignment. 10,000-word practical file serves as the ultimate academic test of this integration. Compiling this file requires executing every layer in sequence. Step 1 is documenting the raw physical elevation data captured by the Dumpy Level Survey. Step 2 requires calculating the Wentworth terrain statistics and plotting the Lorenz curves, based directly on that raw physical data. Step 3 demands mathematically plotting these precise statistical findings using a distortion-controlling polyconic or bond projection. And Step 4 requires accurately interpreting and symbolically mapping the subsurface folds and unconformities hiding beneath that charted terrain. This 10,000-word document functions as a complete, rigorous scientific instrument. True geological mapping is the precise intersection of abstract math, physical measurement, statistical analysis, and structural geology used to decode the planet.